right? I can't see Shayanti yet. Okay, all right. Okay, welcome back everyone. Welcome to the session 3 of day 5 of the VISTA Symposium. And for this session, we have two new moderators, Dr. Shobin Ghosh and Dr. Shayanti Chatterjee, and they are going to moderate our two speakers, Dr. Philippe Schwaller. Please correct me if I pronounce your last name wrong, and also Dr. Hidar Kulik. And with that, I will hand it over to Shayanti.
Thanks, Rajat. So a very warm welcome to all of you in our last session of VISTA Day 5. And so far, we are really overwhelmed by your active participation and support. Once again, on behalf of VISTA, I take this opportunity to convey our heartfelt acknowledgement to all the speakers and our generous sponsors to take VISTA to the height it has reached today. And we look forward to this support in future as well. And in this session, we are looking forward to some exciting talks, and I'm extremely delighted to introduce our first speaker of the session, Dr. Philippe Schwaller, who is indeed a rising star. Dr. Schwaller is an incoming assistant professor at digital chemistry at EPFL, Switzerland. He is currently a postdoctoral researcher in Accelerated Discovery Group at IBM Research Europe. Philippe did his bachelor's and master's degree in material science and engineering from EPFL and completed an MPhil degree in physics at the University of Cambridge. He obtained a PhD degree in chemistry and molecular science from the University of Bern, Switzerland. And since joining IBM Research in 2017, Philippe's primary focus is on machine learning for accelerating the synthesis and discovery of novel molecules and materials. With this, we congratulate Philippe for his new journey as an assistant professor, and we leave the stage to Philippe to take us through the language chemical reactions using transformer models. Thank you, Philippe, and a warm welcome to VISTA.
Thank you very much for this nice introduction and the organization of this great symposium. There have been so many excellent talks so far, and it's really an honor to be here today and talk to you and present my work on learning the language of chemical reactions using transformer models. I will start with a quick outline of my talk. I will first walk you through data, representations, and models, then show you how the models built the background of IBM Reaction for Chemistry and RoboRXN. Then we will explore chemical reaction space together. And finally, I will try to show you what the models learn and why they work. In machine learning, what is always important is the data. And the data I work with is chemical reaction data. And here I'm really grateful to Daniel Lau and also Roger Sale that made available this huge open database of chemical reactions. One way to represent chemical reactions are reaction smiles, as you see here on the screen. And we can take the 2D depiction of this string representation, and you see that you have the precursors on the left separated by the two greater signs and the product on the right. During my talk, I will talk about atom mapping and what I mean by atom mapping, because this is not something that everyone knows, is that every atom in the product is mapped back to the corresponding atom in the reactants. And Daniel already warned us in his dataset description that, while typically correct, atom maps are wrong in many cases. And this motivated me and colleagues at IBM Research to primarily develop atom mapping independent methods. For the next 35 minutes, this here will be the representation of choice, because it allows me to represent atoms as letters and molecules as words. And then after splitting them into sequences of atoms, as you see here, separate the tokens separated by spaces, I can borrow methods developed for human languages and apply them to chemistry. For example, we can cast the chemical reaction prediction task, where we try to predict the most likely product given the precursors, as a translation task. For translation, the typical models used in machine learning are sequence-to-sequence models that aim to translate a sequence in one language, like le chinois in French, to a sequence in another language, die Katze ist schwarz. And they usually have an encoder part that encodes the input, which in reaction prediction, in our case, are the reactants and reagents, computes the most interesting features from that input. And on the other side, you have a decoder that sequentially decodes the most likely product until it predicts an end token, and we know that the SMILE is complete. Those early sequence-to-sequence models had a problem, which was this fixed-sized vector that you see here in the middle. Depending on how complex the inputs were, the encoder could not save all the required information in this fixed-sized vector for the decoder to decode the correct product. So what people in natural language processing came up with is the attention mechanism. If you compare the model architecture to the last slide, what you see now is that the encoder encodes every token independently, saves all those representations in a memory bank, and then at decoding time, the decoder can query this memory bank using the attention mechanism to focus on the most important part to predict the next token. In 2017, Vaswani et al. From Google introduced a new architecture for sequence-to-sequence models, the transformer architecture. And what was special about this architecture is that encoder and decoder weren't made of recurrent neural networks, but consisted fully of stacks of attention layers. And they also introduced a multi-head attention, which, for example, allowed the decoder to look at several important parts of the inputs simultaneously. We adapted the transformer architecture for chemical reaction prediction in the molecular transformer work, and without integrating any rules or inputting some chemical knowledge, this model could accurately predict unseen reactions in standard benchmark datasets. And it's still the best performing model for reaction prediction. When I transitioned from the University of Cambridge to the University of Bern, we asked the question, what is missing in reaction prediction? And two things that were kind of obvious were stereochemistry, which was a weakness of the molecular transformer and not really handled by graph neural network approaches, and experimental validation. And that's when I started working with Giorgio, that you see here on the right, on transfer learning approaches to improve the performance of the molecular transformer on challenging reactions like carbohydrate reactions, as we have seen in the talk before by Kerry. And Giorgio, as a validation, he also performed the 14-step synthesis of a lipid-linked oligosaccharide. And across all the different test sets that we had, we observed huge accuracy increases. And by an accurate prediction, I really mean that every single token of the product molecule corresponded to what was reported in the literature. An example from the JAX test set is this glycosylation reaction here. While the atom mapping is kind of obvious to see, it would even for a human expert be challenging to predict whether it forms an alpha or beta bond and whether it reacts in the axial or equatorial position. And our model was able to predict this. The cool thing with the transfer learning approach that we investigated is that it's applicable to any subspace of interest. So if you have one particular reaction you are interested in, you can fine-tune your model for this reaction class and expect better accuracies. What recently became very popular is our enzymatic reactions, and one question there is clearly, how do we want to represent the enzymes? And I want to show you here the work of David Kreuter, who decided to represent the enzymes as text and pass them as tokenized text, also as input to the enzymatic transformer to then predict the most likely product. There are also alternatives, like the one that was explored by Daniel Probst in this preprint on CamArchive, where he used EC numbers to represent the enzymes. Speaking of back to David's publication, it recently made the cover of Chemical Science, and let me just tell you a few things about the story behind this cover, because the special thing here is that it was generated mostly by a VQ-GAN and CLIP model with a text prompt saying enzymatic chemical reactions, green chemistry, advanced Unreal Engine. And it produced this output here, and we just draw the chemical reaction on top to make it a bit nicer. But yeah, the really cool thing here is the Unreal Engine trick that recently became popular among machine learning researchers that realized that the output of those models, the quality would dramatically increase by adding something like advanced Unreal Engine or 3D rendering or Blender or similar parts. Yeah. Credits for the codes that I've used to generate this image to Katrin Krausen. She has if you're into like generative AI art, please check out her Twitter account. Back to chemistry now. We've used this molecular transformer model also for multi-step synthesis planning, where we try to go from a target molecule and break it down several steps to commercially available building blocks. And for this, we trained two transformer models, one retro model that would go back one step and suggest possible precursors, and then another one, a forward prediction model, which had the role of ranking the different steps. What makes our approach different from other approaches in literature is that we do not only predict reactants, but also reagents, catalysts, and solvents. If you compare to what the amazing work that we have seen by Segler and Colley that mainly focus on predicting the reactants. Another problem or another thing that we always have when working with chemical reaction data, and in particular those open source data set, is noise. And here on that slide, I would like to point you to the excellent work of Alessandra Toniato, who looked at the prediction at every epoch during the training and basically looked at forgetting events that would happen when the model correctly predicted a reaction, then again wrongly predicted it in the next epoch, and so on. And using this signal, she then automatically cleaned the reaction data set without really human intervention. At IBM, we're really proud to make our AI models for chemical reactions accessible. And we do this through this IBM Reaction for Chemistry platform, which is free. And the great thing there, I guess, that it gives access to this model to people without coding experience. So chemists can simply go there, can draw molecules as input and run predictions using our models and see what the AI models would predict. We have also the retrosynthesis feature available, and where you get back different suggestions of synthesis rows. It's even available in an interactive mode. In the interactive mode, the chemists get suggestions by the AI model and then can select using their expert knowledge which of the steps they want to take. And they can further expand the molecules they are interested in. Here's some user feedback that we got 2019, and for this, because I forgot to share my sound, I quickly have to unshare my screen. Sorry for that. I guess I'm back. Can you see it?
Hello, my name is Alessandro.
Oh.
Alessandro Castrogiovanni from University of Basel, and today I want to show you how I use IBM Reaction for my everyday research. And I selected for you molecule to synthesize, and the program is giving me the retrosynthetic pathway, the most convenient retrosynthetic pathway. And for example, in the case of this ketone, the program is telling me how to prepare it with halogen metal exchange, and then addition of the lithiated species to the acyl chloride, and then the protection of the ether with pyridinium chloride to deliver the product. But this is not just the only result. There are other outputs given by the program, and I would show you another one. In this case, they do the halogen metal exchange on another substrate, and then they perform the oxidation with manganese dioxide and deprotect. And in my opinion, everything makes sense, and this is helping me and my colleagues to achieve the substrates, the synthesis of every substrate.
Such feedback kept us motivated to always continuously improve our models. And
hello, my name is Alessandro.
I'm somewhere. I'll get that. Okay, yeah, so I got back into control of my PowerPoint presentation. So what's next? And if you had a look at Theo's talk last week, so you already know about RoboRXN, which I will just quickly introduce on the next few slides. Imagine you're a chemist at home and you do all the creative process of designing a molecule. Then you connect to the cloud, where you get access to a synthesis planning tool that, like the one I've described on the last few slides. But not only that, you can also have a model that automatically converts the different reaction steps in your synthesis into actions that then can be performed by a human, but also by a robot. We have a prototype of such a cloud-connected synthesis platform in IBM research in Zurich, and collaborators from all over the world, even from the US, have already successfully synthesized molecules through this platform. Here I'm just showing you a synthesis of a photoacid generator. One of the fundamental parts behind IBM RoboRXN is the smiles to action model developed by Alain Vaucher. where that is able to transform arbitrary chemical reactions represented as smiles into those sequences of actions that can then be performed by the robot. And at this point, let me just show all the whole team behind RoboRXN, led by Theodoro Leino. In the first part of my presentation, I've shown to you reaction transformer models that convert a sequence of atoms into another sequence. For example, for reaction prediction, we converted the precursor molecules into a product, and vice versa for retrosynthesis. We converted target products into possible precursor sets. Even the SMICE to action models I've mentioned on the last slide is using a sequence to sequence transformer model. From now on, in my second part of the presentation, we will use another type of transformer models, an encoder-only model. And this model will get as an input a complete chemical reactions, so precursors and products, and then we will use it to do reaction classification or yield prediction. So predict a single value or label. Let us first zoom into such a reaction transformer. So a transformer model encoder is made of self-attention layers, stacks of them. What it gets as an input, as I said before, is a tokenized reaction smiles. Every self-attention layer then has multiple heads to learn different functionalities to attend the different input tokens and learn better and better contextual representations. Why is context so important? Let me make an analogy with human language. If you think of the word bank, then the word bank has a completely different meaning whether you speak about the riverbank or the bank you get money from. And similarly, in chemistry, if you look at this reaction here, if you look at the individual atoms, nitrogen atom will have a different meaning depending on the closest, on the neighboring atoms, the atoms in the same molecule, and also the complete chemical reaction. Afterwards, what we can do is add a regression or classification head on top, and then train this model on a downstream task like reaction, yield prediction, or classification. The training of those models typically happens in two stages. First, the pre-training stage, and then the fine-tuning. For pre-training, what I typically use is masked language modeling, where we basically mask out different tokens in the reactions and then let the model predict those randomly masked tokens. It's a reaction corruption task for which we can generate quasi-unlimited training data. And to perform well on that task, the model has to learn some kind of chemistry, but also the SMICE grammar. We can randomly mask all the tokens and so on. Then as a downstream task, we can, for example, tackle reaction classification, where we want to go from a reaction representation and predict the most likely reaction class, the main reaction. And on data from NextMove software, we could show that our models were 98% accurate or more on unseen reactions. But what is even more exciting for me is when you take away this last layer of the model here, then you can take the outputs and use them like as a reaction fingerprints, as Shell in the presentation before already nicely introduced. What we made with those reaction fingerprints are those chemical reaction atlases, and we could show that they were able to almost perfectly cluster chemical reaction space. The algorithms for the dimensionality reduction and making those maps was developed by Daniel Probst during his PhD. Here you have an example of an interactive reaction atlas, where we can display categorical properties, but also continuous properties, and get a feeling of the local but also global trends of our reaction dataset. We can zoom into the reaction atlas and display different reactions, highlight additional information, and so on. And it gives us a new way of exploring chemical reaction space. The reaction fingerprints can also be used to search for similar reactions. If we take this Mitsunobu reaction here as an example, then those would be the closest neighbors. And they not only have the same reaction centers, but they also share similar reagents, as you can see here. The code is available in open source. You can just pip install it after installing RDKit. And as we've seen in this VISTA conference, it has already been used by different groups. I would also like to thank the authors of this reusability report, if they are online on this talk, because they actually retrained our models on the internal data, and it seemed to work well as well. Another downstream application is the prediction of reaction yields. And here we'll focus on the dataset from Abby Doyle that presented last week, and her amazing work on using DFT descriptors and random forest. And last year, we also seen the multi-fingerprint features plus random forest models by Sanford and the Glorious group. And we basically asked the question, how far could we get by showing the model only reaction spikes and not computing fingerprints directly with through this reaction encoder models. And we were kind of positively surprised to see that our models were able to learn to predict reaction yields in this data set remarkably well just by seeing the smiles. The other thing is that we explored is the low data regime, because usually when you imagine such a large neural network model, you think it's so data hungry and it will never perform well with fewer data points. But through this pre-training and then fine-tuning scheme plus additional data augmentation, we were able to match the DFT descriptors even for training data sets as low as 98 data points. The natural question then is that arises then is, but why do transformers work so well in chemistry? And that's when I teamed up with Ben Hoover and Hendrik Storwald from the IBM MIT lab in Cambridge. And what we did is to train a reaction transformer model just on this reaction corruption task on millions of unlabeled reaction spies. And then we applied visual inspection to investigate what the model had learned from this reaction. Here, it's important for you to see that our model that we investigate here has 8 heads in 12 different layers. And we can basically look at all the signals that the model had learned in all those individual heads. And we can take a reaction as an input and then highlight what the head would have learned for this specific reaction. And this is kind of a confusing plot at first, but what you see here is the input reaction on top, tokenized as smiles, and the input reaction also on the bottom, and we split it in two so that we can show the attention weights. So what was important for the head to learn this better representation in the middle. And in this case, we highlight the attention that goes from this atom here, and it goes mainly to the neighboring atom. And we can do this for different heads and layers, and we see different attention patterns appearing. And we went through our trained models, and at some point we found a head where the pattern looked the following. If you look closely here, you see that precursor atoms mostly focus on product atoms and vice versa. Product atoms focus on precursor atoms. And if you remember the beginning of my talk, this sounds really a bit like this atom mapping. And indeed, we discovered that every model, transformer model we trained on chemical reactions with this task had learned atom mapping, basically how atoms reconfigure during a chemical reaction. And we use this signal to build Reactionmapper. Reactionmapper, as the name probably already tells you, it's an atom mapping algorithm, and it works as follows. We get the attention weights from the model, then we iterate through the product atoms, when we map the most likely pair, for example, the number 3 here to the number 3 here, and then we increase, because we know that product atoms that are close together will likely also be close together in the reactants. We increase the attention from the newly mapped pair neighbors in the product to the neighbors in the reactants. And with the pure attention, we already get 96% correct maps. And with this neighbor multiplier, the performance even increases to 99% on a test set of 49 reactions published by Schneider et al. The question is, has Reactionmapper learned some chemistry? And for this, I would like to show you the following example that a user sent to us and said, Reactionmapper doesn't work. Reactionmapper doesn't even map the benzene ring to the benzene ring. We were a bit puzzled to see this, and we inputted it into our system, looked at the attention weights, and if you look here, most of them are just straight. So there's no, it's basically Reactionmapper telling you this is not valid chemistry. And as soon as you make the input reaction slightly more chemically reasonable, then you recover back this nice atom mapping pattern in this head, and it also maps the reaction correctly. For the experts in the audience, this is maybe a slightly more challenging example that would require you to draw a few intermediate steps. So I will just show what was proposed in the original paper. And Reactionmapper was able to correctly map this reaction. The atom maps are not only accurate, but we map also at fast speeds, like 7 milliseconds per reaction, which allows us to map huge reaction data sets. And then we can extract reaction centers, bond changes, basically the grammar of chemical reactions. And this can then be used to, for example, improve synthesis planning tools, make quantum mechanical simulations possible or easier, and also increase the accessibility and interpretability of reaction databases. On the next slide, I will just show you how atom mapping affects synthesis planning. So we've seen in all those talks and at this conference, the work by Marvin Segler and by Connor Colley, and there's also lots of template-based work by the people at AstraZeneca. We have graph neural network-based approaches that predict bond changes and graph edits, and also the smiles to smiles approaches that I was presenting to you in the beginning of my talk. The two first methods are atom mapping dependent because they use the atom mapping to generate the training data. While we are atom mapping independent, but we have the disadvantage, the slight disadvantage that we do not track the atom rearrangement during the prediction. And this would be a feature that is nice to have to increase the interpretability of our predictions. So in the end, if we have a better atom mapping tool, I think that all those synthesis planning approaches benefit. If you want to try Reactionmapper, please go on reactionmapper.ai because we have a demo there, and we're super happy that the group of Alexander Barnek, who also presented at this conference on Friday, recently uploaded a preprint on CamArchive, which selected Reactionmapper as the best tool in an atom mapping benchmark, even better than some commercially available tools. Also for this, we have open source code available, so you can pip install the thing. And it was recently published after a long time in Science Advances, and yeah, we super happy that it also made the headline of the CNN newsletter. And again, many thanks to Marvin for always highlighting this work. I guess more than half of the altmetric score comes from one of his tweets. So thank you for that. And here, just a quick summary of my talk. In the first part, you've seen encoder, decoder, transformer models that we've used for reaction prediction, synthesis planning, the prediction of experimental procedures, and also the noise reduction in reaction datasets. In the second part, we turn to encoder-only transformers for classification in fingerprints, reaction yield prediction, and atom mapping. If the main takeaways of my talk is probably that if you're open for maybe the unusual representations of your data, but that allow you to borrow methods from other fields that are really developed, then sometimes you get kind of remarkable results in your field. And I think I could I hope I could show to you that language methods can be applied in chemistry. And we have this IBM Reaction for Chemistry platform that is free, even with API access. So feel free to try it out. We have reaction prediction, synthesis planning, and many more tools online. If you are interested in exploring your chemical reaction dataset in a new way, try our tutorials for the reaction fingerprint and reaction atlases. And I guess the most, what I found the most mind-blowing in my PhD, the most mind-blowing results was really that we were able to find those atom mapping patterns in what the transformer models had captured from unlabeled chemical reactions. And we were able to use this signal to build Reactionmapper. At this point, I want to point to Theodore Leino and Jean-Louis Raymond, my two PhD supervisors, and all my amazing collaborators, which made all this work possible. And also kind of all the libraries that we use on a daily basis to develop those models. You've heard it in the introduction, what's next for me. So I've just been recently, last Thursday, appointed as assistant professor at EPFL. So I'm super excited about that and looking forward to this next challenge. I'll be starting early 2022, and I'm looking for PhD students. So if you're interested, ping me on Twitter or write me an email. Related to the NCCR catalysis that my group will be part of, there's an open position at ETH in Zurich. And yeah, if you're interested, please write to Javier Perez in ETH, who is the director of the NCCR. And at this point, many thanks for your attention. It was really a pleasure to be part of the speakers at this conference, and I'm happy to take any questions.
Thanks, Philippe, for such a wonderful and informative talk and for taking us through this language of chemical reaction. It was really exciting. And we have quite a number of questions. So first, let us begin with the question. Showman, can you begin? My
Sure.
screen just had.
Yeah, sure. So Navneet asked, nice talk. Was curious to know how does the retrosynthetic model perform on novel small molecules that are diverse in comparison to the training set?
This is this is a very interesting question. So I guess natural products would be still like out of the reach of the retrosynthetic models. Then we've tested a range of small molecules, and it's sometimes they really work surprisingly well on those molecules. And I guess what is most important is that reactions that make them accessible are somewhere available in the training data. And then you have other challenges that are like the molecule, the library, because in retrosynthesis, you want to break down your target molecule into commercially available building blocks. So the results very much depend on the library that you take for the commercially available building blocks as well. So then the success of retrosynthesis will depend on a lot of factors, but if you have a specific example in mind, please feel free to try it on IBM Reaction for Chemistry, even in the interactive mode, and then you immediately see the results that the models come up with. I think the retrosynthetic models that we have now are really interesting for idea generation. They can come up with suggestions that maybe an organic chemist would not have come up, because also humans are some kind of biased towards a specific reaction space, maybe where they had most successful reactions in the past. And so those machine learning models that are trained on a vast chemical reaction data can come up with alternative suggestions that extend the ideas of the chemists.
Okay, so something in similar line, I will have a question. First, he thanked you for such a nice presentation and how you prepare reaction classes for training models. Databases usually do not contain information about reaction classes. So is it human manual markup?
Okay, yeah, this is a very good question. So in our work, we explored two different reaction class datasets. So first we had the reaction classes provided in the Pistachio database by Nextmove Software. But this is a commercially available dataset. So what we then made is our own reaction class dataset, which is called USPTO TPL for template, because we used Reactionmapper that I've presented in the last part on top of the open reaction database, and on top of the patent data, and then we extracted the 1,000 most common templates in there and basically assigned the classes using the templates. So this is an open source reaction classification data set that you can get from our GitHub if you go to Reaction for Chemistry, then Reaction FP. Yeah.
Patrick asked, thank you for your great talk. in your transformer model, do you use simple positional encoding for the tokens in the smiles? Have you tried encoding that takes into account the graph structure?
This is an amazing question. This is really, so far we only use positional encoding, and it works already quite well, but I would expect to see improvements if you somehow embed the graph structure in the encoding. So this is definitely a very interesting direction to go. Yeah.
Okay, so Shahil has a question, soon to be Professor Schwaller. He already claimed you. And I got a question that how do you handle compounds for which there is a retrosynthetic pathway possible, but the compound cannot be synthesized or non-synthesizable in practice? Is there some sort of feedback we can give it back to the transformer model?
This is, so you mean you would predict a synthesis route, and then you would try to perform it in the lab, and one of the steps would fail. Then you could potentially go back to this this specific step and try to exclude this particular molecule and rerun the prediction without having, excluding that molecule. I guess this would be a way how you could do it, but there are certainly more intelligent ways to approach this. I guess, but this feedback loop should definitely be implemented in the next version of those retrosynthesis tools. Yeah.
Okay. There is one. Okay. So one question from Bo Zhao. Thanks for the talk. I have a question. Does the reaction smile string missing some of the chemicals like solvent or additive influence the model performance?
I would, I would say so. Ideally, we would always have a maximum of information available. What is the problematic in some of the reaction databases is that exactly this information is sometimes missing. And if you do not really clean the reaction data and you look for those specific cases, let's take a bromo-Suzuki coupling reaction. If it appears one time with a palladium catalyst and another time without a palladium catalyst, the problem will be that the model will learn that the palladium catalyst is not important for the reaction to happen, and then start predicting the same output with or without palladium catalyst. So this is a tricky thing with the reaction data and cleaning it. Yeah.
Okay. So another question from Nikolai. First, really great talk and congratulations on your new position. So with respect to the language model, does prediction accuracy depend on the positional entry of the different reactants? Like in normal language where meaning of a sentence depends on how you formulate it?
That's again a great question. If you, for example, if we go back to the yield prediction, so you can actually make use of different representation of your inputs to do data augmentation and for you to increase your data set. And okay, in this case here that I'm showing on this graph, we randomized the different input smiles, but we didn't change the position. But in the same work, we also explored how the performance of the model improves when you augment your training data by shuffling the different molecules, and it actually improves over a canonical ordering of your molecules.
Okay.
I think there is one question from Andreas. Again, he congratulated you for your new position and your work. So his question is, how would you tackle the fact that the chemical space is highly biased towards some popular reactions? What do you think would be a good way to introduce exploration into models?
That's again a very good question. I guess at some point we have to come up with models that, okay, we have to get data for also negative data for our reactions, and try to use the negative data to somehow improve our models. And how can we, this is, I think this exploration is more like something that we try to tackle when we do retrosynthetic predictions, because in the end, highly biased models that always predict, I don't know, protections and deprotections, because there are so many in the reaction and the pattern reactions, are not really useful in a multi-step retrosynthesis setting. So we try different ways to like train models that are less biased towards a specific reaction class, and by different weights of on the different classes, and and so on. We have some work going on that, and this is I guess something that has a lot of potential to improve multi-step retrosynthetic approaches, if we decrease the bias in the data and make the model explore more.
Okay, so maybe we just quickly take one or two more questions. Really inspiring. John Lopez says that it looks like the transformer do not use information like temperature, concentration, reaction time, which are important for the yield. So could you please comment on this?
Yes, definitely. Yeah, no, but that's correct. In this experiment that I've shown, the reaction conditions were held constant, so those reactions were comparable, and the transformer didn't have the information of for example, temperature. But I guess this is if we try to have global yield predictors, I think the information about conditions like the temperature, also the pressure, it's really important to include in the inputs of the transform model.
Okay, so thanks a lot, Dr. Schwaller. And with this, maybe if you can just look into the chat box and answer a few more questions
Yes.
there. And so with this, I hand over to Showman to invite our next speaker, Professor Kulik.
Thank you very much for having me, and I'm very much looking forward to
We are delighted.
Thank you.
I'd request Professor Kulik to share her slide while I give a brief introduction to her. Professor Kulik received her BE in chemical engineering from Cooper Union in 2004, and her PhD in material science and engineering from MIT in 2009. She performed her postdoctoral research at Lawrence Livermore in 2010 and at Stanford from 2010 to 2013. She came back to MIT to join as a faculty member in 2013 and received tenure in 2021. Her group's research at MIT leverages computational modeling to aid the discovery of new materials and mechanisms. Professor Kulik has received many awards during her career, including NSF Career Award in 2019, the ACS Comp Division OpenEye Award for Outstanding Junior Faculty in Computational Chemistry, a Solon Fellowship in 2021, and many more. With that, I will leave the space to Professor Kulik.
Thanks. Thanks for the kind introduction and for the invitation to speak. So as the introduction mentioned, I'm a computational chemist by training, and I'm going to be taking us through some work my group has focused on in the past 5 or so years in developing techniques for the accelerated discovery of new materials, specifically open shell transition metal complexes. And you know, when we first got into this, we wanted to leverage all of the tools of language. And back then, this was around 2015, and we were thinking in terms of the language of cheminformatics. And so we were thinking about, how do you go out and explore a combinatorially vast space? So people like to make comments about how big organic molecule space is, but in comparison, if you think about what could be going on in a space of transition metal complexes, there's a really even considerably larger space to think about exploring, because we have to think about the ligands and metal combinations and spin and oxidation states, and the sheer size of some of these molecules. So if we're looking for the optimal molecule to imagine satisfying our design objective, if it's a material that we want for, say, potential redox storage, or if we want it for photocatalysis or chemical catalysis, the right answer could be any one of these needles in a haystack. And so we were thinking about what ways do we build a language up specifically for open shell transition metal chemistry to take computational chemistry away from this service tool where someone hands us a material and tells us to characterize it with DFT, but instead to start to build up an understanding atom by atom. And so you can imagine that the atoms that matter most really depend on the property involved. And this specific concern is something that's highly quantum mechanical in nature, because the metal can have different magnetic spins and oxidation states, and where the electrons are really matters. But it also depends on the property we want to predict. And why do I care about this as a chemical engineer? Well, because a lot of the catalysis that you've been hearing about in this workshop happens at single metal sites, either in materials and heterogeneous catalysts, in MOFs, in homogeneous catalysts, also challenges for thinking about how do we optimally store energy in redox couples, or think about things like gas separations. All can be exquisitely tuned if we know how to engineer these metal sites from first principles. And so hopefully I'll get a chance to touch upon each of these today. But what we wanted to do first was just take inspiration from tools that naturally work in organic chemistry, things like SMILE strings that you've just been hearing about, force fields and semi-empirical theories, large databases, including the GDB, but also including zinc and PubChem, and concepts of molecular similarity. The challenge is that when you go to open shell transition metal chemistry, all these tools that routinely work in organic chemistry fail. And they fail pretty catastrophically. So if you look up which are the best in class force fields and semi-empirical theories that can predict open shell transition metal complex properties in a spin state dependent manner, none can. They don't exist. DFTs are bottom rung, and anyone who's run a DFT calculation on a porphyrin can tell you that DFT is probably too low for a bottom rung. And so the kinds of computations we can do from a physics-based perspective are quite demanding and quite error prone. Then things like SMILE strings require knowledge of spin and oxidation state dependent bond lengths and structures, all of which are not adequately encoded even in the SMILES language. And the types of databases we can go out and look at are things like the Cambridge Structural Database, which I will touch upon today. But basically what they'll tell us is where people have been, not where we should go. And they'll tell us that of the relatively small space of all possible transition metal complexes people have visited certain neighborhoods a lot. They've visited porphyrins a lot. And then concepts of molecular similarity that routinely work for organic chemistry will fail for transition metal chemistry. They don't encode the oxidation and spin state dependence of relationships and materials properties. So not daunted by this, we took a divide and conquer approach, recognizing that a lot of a transition metal complex is organic in nature. And we first started out on this, I guess, about 5-6 years ago. But what we wanted to do was take what really worked really well in organic chemistry and bridge it with what was going to fail for open shell transition metal chemistry. And this was motivated by the observation that force fields work really well for organic bits. And that's because the relationships being encoded for organic molecules are very trivial. So the movement from a triple bond to a double bond to a single bond is highly linear in nature in an organic molecule, whereas for open shell transition metal complex, just changing the spin and oxidation state of the metal can easily change the metal ligand bond length more than it changes in an organic molecule, and in a highly nonlinear way. So the first time we did this, we took a divide and conquer approach using organic chemistry and cheminformatics where it made sense in the organic parts of these molecules, and a database of DFT values that we later replaced with an artificial neural network for the metal ligand bond lengths. And we enabled the automated command line structure generation of open shell transition metal complexes and catalysts using the language of things like organic SMILES libraries like Chembl, and exploiting concepts of similarity and dissimilarity for just the organic ligands around transition metal complex. All of this is in our open source code. Also, there's a web version of it available online. And this will be the glue underneath everything I'll talk about for the rest of my talk today. So the first thing we did with this is we didn't go out and explore the universe of transition metal complex chemical space, but we did go out and visit little neighborhoods. And every time we did, we found surprising ways to break intuition, break expectation, and applications of this included from thinking about how do we accelerate and control the synthesis of quantum dot materials over to understanding how to break so-called scaling relations in transition metal catalysis. And in all cases, just by varying the chemistry a little bit wider than had been varied previously in the literature, up to a scale of around 500 catalysts or 200 materials, we were able to uncover design principles that weren't visible from published work or from past knowledge, and would require going out and doing this type of exploration. And in a lot of cases, all we did was we simply threw out intuition, threw out past experience and looked at these spaces. But these things like these 500 catalysts, they still took us months at a time. So we were computational chemists, and each of these points represents a DFT calculation or series of DFT calculations we were carrying out. So it quickly led us to the point, to this question of what are we going to do to actually go out and explore these larger spaces, keeping in mind that semi-empirical and force field level models are not accurate enough in this space. And so we quickly concluded that we needed faster than high throughput, but that there's specific challenges to open shell transition metal complex space because the range of materials and sizes we want to study is very vast. It's very sparsely populated in the past in terms of where people have gone out and synthesized ligands. Things like the metal spin can be controlled and electrons can be paired or unpaired. The metals that we want to study can sample a wide range of oxidation states. And so thinking about how we even represent that. And so we were, what is clear is that the challenges and the opportunities for us in thinking about how to represent open shell transition metal chemistry to a machine learning model are distinct from how people think about organic chemistry. But at the time when we got into this, people were only thinking about organic chemistry. And so we knew we needed to make different choices, but we didn't know how different those choices should be or what nature they should be. And actually, the first way we got into this was we had MolSimplify working, but my student, Jean-Paul Genet, who since defended his PhD last year and is now at AstraZeneca, I was pleased to see his name in the previous talk on a reproducibility report. It's and so, but in any case, he came to me and he said, I have a homework problem. I need to train a machine learning model. Is there anything that you'd like me to predict? And I said, absolutely. I'd like you to predict the quantum mechanical ground state spin of a transition metal complex. And I'd like you to predict the spin splitting between that ground state and then the next lowest state. And because I know we're going to use DFT training data, this is a property that would be hard to access experimentally as well. But because I know we're going to be using DFT training data and I don't really trust DFT at all, I also want you to predict how sensitive the result is to the exchange correlation functional we used. And then I don't want you to use any geometric information, but I want you to be able to predict the metal ligand geometry for me so that we can put that into our mole simplify code. And the spoiler alert is that all of this worked, and we then generalized it to things like redox potential, HOMO-LUMO gap, catalyst reaction energetics, and so on. And we worked with very small data sets. This was on the scale of one homework assignment back in 2016 and what we could generate on our cluster. We worked with mononuclear octahedral transition metal complexes that are highly relevant as catalysts, metals in multiple oxidation and spin states. We addressed the exchange correlation sensitivity challenge by sampling a range of Hartree-Fock exchange fractions, because that's the piece in DFT that transition metal complexes are the most sensitive to. And our data set sizes were really small, not as small as some experimental data sets, but in comparison to things like the QM9 data set, the large size and variability of our transition metal complexes mandated that our data set size was considerably smaller. So we thought about what other people were doing in organic chemistry, and we knew that a lot of people were working on representations that encoded what I, as a computational chemist, would normally think about doing, which was take all of the atoms, all of their positions in space, and use all of that information as well as their elemental identity and pass it to a model. But we knew also that there are a lot of heuristic theories in open shell transition metal chemistry that throw almost all of that information away, focusing instead only on the metal and direct coordinating environment. And the right answer probably sat somewhere between the two. So the first way we did this for the homework assignment was I sat down as a skeptic of anything to do with ML and thought about everything I knew about a transition metal complex. And I knew the metal environment matters, so the coordinating atom and the metal identity. We knew from some DFT work we had done that things like differences in local electronegativity are really important. And we dug into the cheminformatics literature and found the Cure truncated shape index seemed to be a useful way to represent rigidity. And we were interested in a no-cost series of ad hoc descriptors, and we knew that we had to bias things towards being more metal local than a conventional representation would have at the time. But we also knew that a lot of people in the community were interested in predicting things like atomization energies, which would depend strongly on the number of atoms. And so we weren't very satisfied with this, and we went back and looked at how we might have a more systematic approach to doing the same series of representations, and both of them worked, which is why I still talk about them today. But we adapted Moreau-Barodo autocorrelation functions, which are products on the molecular graph of heuristic descriptors such as nuclear charge and topology. And we adapted them for open shell transition metal chemistry, knowing that where we're focusing on the molecule was pretty important. And the motivation for doing it this way was because these types of representations can be used with any number of machine learning models, from random forest to kernel ridge regression models to artificial neural networks, rather than using graph convolutional neural nets, but it's basically the same thing in the end. And so we have adjustable depth in our revised autocorrelations, and we also introduced differences. And so things like the number of atoms in the system map back to the zero depth identity. The coordinating atom is the ligand-centered Z zero depth rack. And then even things like the electronegativity would be the one depth ligand-centered difference chi rack, and so on. And so when you see me color these, I'll color the nuclear charge and electronegativity as more electronic in nature, topology and identity more geometric in nature. But just keep in mind, these all come from a lookup table. So I will actually show how we've used these representations to machine learn on not just DFT data, but on experimental data, as well as on data from other simulation sources. So there's no prior computation from a DFT perspective required for using this representation. And when a particular feature only depends on information close to the metal, we call it proximal, and when it's distant, we call it distal. And so a PCA shows pretty clearly why it's important to do this and why it's important to allow for a representation that throws away a lot of the distant information. So these two transition metal complexes I'm showing at the bottom left have very different sizes, but very similar properties. And so a whole molecule representation does a great job of clustering these molecules by size. but one of our local representations puts the two molecules much closer together, making a lightweight machine learning model work a lot less hard to learn the same property. And so the result was, even with our ad hoc descriptor set, we were able to predict the quantum mechanical ground state spins of these molecules. Now, this is something that no semi-empirical or force field theory could really do, certainly not in this general way, and we could do it in a DFT functional dependent manner. And in the cases that we did get wrong, the few percent, it was cases where the states were near degenerate. And the result was also that even on the same data set size, we were able to get an order of magnitude smaller error on the same data set. And so what this meant was we were able to predict to close to the DFT result from our neural net in about a second if we trusted it, where the conventional DFT calculation would have taken us hours to days. And so I show MCDL25 side by side with RAC and feature selected subsets, where our RAC's feature set, our default feature vector is about 155 dimensions. You might expect that it was outperforming MCDL25 from about 2.5 kilocal per mole mean absolute error down to 1 kilocal per mole mean absolute error, just because it's encoding more information and resulting in overfit models. But when we applied feature selection, we could get down to similarly sized feature vectors similar to the sparse nature of MCDL25, where MCDL25 is in fact very metalocal and generalizes well because it is so sparse. And we did this without any loss in accuracy. So now when I said we were within a few kilocals per mole of the DFT answer, we actually got down to about 1 kilocal per mole within the DFT answer. And that is powerful if we want to go out and do that large scale chemical space exploration. So maybe you're not that interested in adiabatic spin splitting, you're not that interested in designing materials for quantum information science or as molecular magnets and sensors. So maybe you're more interested in redox potential. The same general trends hold. And we also showed that we could do this to go ahead and think about doing things like replacing force fields. So I mentioned force fields can't predict the metal ligand bond length of these transition metal complexes, but with our neural net, we now could predict the metal ligand bond length to within 0.01 angstroms. And it makes sense in the end because the neural net is more able to encode highly nonlinear relationships that couldn't be encoded in analytical functional forms like the universal force field. So we wanted to take a look at why it was that my ad hoc representation that, really encoded what I thought I knew about how a transition metal complex worked after about a decade of running DFT calculations on them. Why was it so easily outperformed by feature selected subsets of RACs? Well, this is what MCDL25 looks like in terms of proximal, middle, and distal features. RAC 155 by definition encodes a lot of non-local information just because that's how the products and differences work out. And when we apply feature selection, we can see that actually the smaller URAC subset and MCDL25 subset agree that distant features are in fact uninformative in terms of making these property predictions. But where the two differ is that there's a more balanced treatment of proximal and middle features in URAC 26 than there was in the one that we came up with for MCDL25. And that's largely just because we lacked creativity. So maybe if you don't trust DFT as far as you could throw it, maybe you're not that impressed that we can come up with a prediction in a second that would have taken us hours to days. But what we like to do early on is take a look at using random forest ranked recursive feature addition, what features are most important to make property predictions. And this is going to be an abstraction here on a porphyrin. And what I'll do is I'll color atoms again, more blue if more electronic descriptors are essential for them, yellow if more geometric descriptors are important. I'll make them large if they are important in the prediction and small if they're unimportant. So the spin splitting larger set on the left is just related to, it's a superset of what's in the spin splitting URAC 26 set on the right. And both of them tell us just that our approach has learned that ligand field theory works, that the metal and atoms close to the metal matter most in terms of making predictions about the quantum mechanical ground state spin of a molecule. But where things get interesting is when we contrast this with what else lights up. If we look at the bond length, the what it takes to predict the metal ligand bond length or to predict the redox potential of the molecule. In fact, with redox potential, we get a whole entirely different part of the molecule lit up, and it indicates to us that redox potential is strongly size dependent. And this now gives us a map, not just to making faster property predictions, but to think about the orthogonal design of materials. We can design one part of a molecule to tune its redox potential and another part of a molecule to control its quantum mechanical spin. So I'm going to show this on other materials, and the pie charts turn out to be a little bit easier to read than the abstraction. So when I show them as pie charts, just to note that this is what they look like. If we see a lot of gray, then this is a highly non-local property we'd like to predict. If we see a lot of blue and red, then it's a highly metal local property to predict. And I would say that this has been one of our biggest contributions, is thinking about how do we go about and engage in design in this way by looking at representations and looking at the selected features over data sets. So this would be bad news, of course, if these pie charts were strongly dependent on the data source, if they're strongly dependent on the fact that we use one DFT functional to generate them. So I hope to come back and convince you that these are actually incredibly robust to the method used. But naturally, everything I've described so far, there is some uncertainty. There's uncertainty of, if I'm as a computational chemist using machine learning to go out and do accelerated discovery in transition metal chemistry, how much is a lead molecule I come up with on a computer sensitive to the level of theory I use to generate that training data? Then there are questions that I won't have a chance to talk about today, is when we let machine learning models go out and accelerate the discovery of new materials, how many times will a calculation fail, and how will we know it's failed without intervening directly? And then another thing I won't have a chance to say much about today, but something that we were very concerned with was model generalization and uncertainty quantification of the model. So back to the pie charts. And normally, if you've ever peered into one of our papers, or if not, we tend to use global hybrid DFT, which is certainly not the best in class DFT functional you could ever imagine using. So we wanted to ask ourselves recently, does it matter which exchange correlation functional we choose for this? And the answer is no. So if we look at the adiabatic spin splitting on 23 different density functionals, spanning from very affordable semi-local generalized gradient approximation all the way up to double hybrids, which include MP2 correlation and long range, all of these functionals tend to agree, even ones we would think wouldn't agree because one, we might have a bias and a perception that it's better than the others. They all pretty much agree, even in cases where we can pick on one M062X and we can see that it's behaving differently from all the others. And spin splitting is a very functional sensitive property. We can see there's still a lot of structure here. And so here is a UMAP in the latent space of one of our neural nets trained on about 2,000 points from each of these functionals. And what we see is that all of the functionals actually agree on both the very high spin splitting points and the very low spin splitting points. And the only disagreement here arises in the mid-range. And that's bad news only because those are the most interesting materials from the perspective of being able to define and design switchable spins in what's known as spin crossover complexes. So for the sake of this talk, I'm going to define a spin crossover complex as something where the high spin and low spin are within 5 kilocals per mole of each other. These are the materials that have the greatest chance of changing their spin state in response to temperature or light. They're functional materials that can change their optical properties. So they're really useful and interesting as sensors and so on. So if we group together all the semi-local functionals, all the hybrid functionals, all the double hybrids, and we ask, to what extent do any of them have a consensus agreement on what makes a spin crossover complex? You can see that here, there's very little overlap. So semi-local functionals, which have well-known biases, don't agree with the other functionals about what it takes to make a spin crossover material. But I'd like to point out that this is strongly sensitive to the property we pursue. So if instead I looked at homo-lumo gap of these same materials, you can see the overlap is much better between all these different functionals. And so this really, we've really picked one of the most challenging things to get right from DFT, and have found that there's a lack of consensus. But back to the pie charts. So I told you the pie charts were one of the biggest contributions I felt we had made. And so are the pie charts that sensitive to the functional we chose? Because really, it's really hard to know beforehand what is the right DFT functional to use in this type of material space. There's no right answer, unlike organic chemistry, where we can march up a ladder to chemical accuracy heaven, or we can rely on someone to get a really robust experimental result. There is no ground truth ultimately when it comes to knowing beforehand all of the soup and all the stuff that's going on in terms of these types of challenging materials. So picking on a GGA here, B-lip, this is the adiabatic high spin, low spin splitting. This is exactly what I showed you before. It's very metal local in nature. Global features don't matter much. And if we go over to something like the vertical IP, which is closely related to the redox potential I showed you a few slides ago, these features become much more global in nature. And so we could ask, is all of this just an artifact of the DFT functional? Would it have changed if we changed the functional? And so we can go over to even functionals like M06L and M06-2X that didn't agree that well with the other functionals. And we can see that the pie charts are actually pretty invariant. So this is great news. The differences we see that are qualitative in nature between predicting properties like spin and redox potential that told us we could tune one without changing the other, or vice versa, those hold up. And even the character of those particular selected racks hold up. So this gives us a path now to thinking about using the cheapest method, the cheapest basis set, and a lot more of that is outlined in this archive preprint at the bottom here. And use that to come up with these design principles, and then go out and use these maps still to then carry out higher level calculations. Because in fact, these pie charts are invariant. Even if we go to the expensive first principles double hybrid that costs us probably at least a couple orders of magnitude more to carry out, the pie charts really are not changing significantly. Certainly not in a way that would change how we would go out and design these materials. So in terms of thinking about other ways we could exploit neural networks for carrying out accelerated chemical discovery, one of the first ways we did this was think about discrete optimization in a candidate pool, and trying to know that our neural nets trained on relatively small data sets require some knowledge of where they're uncertain, combined with some optimization algorithm to tell us where to find the best leads. And this was a high school student in my lab, Lydia Chan, doing a summer project several years ago. We decided to implement a genetic algorithm. There's nothing special about genetic algorithms, except that when we exploited our neural net, we used it to evaluate fitness of the compounds, and the result was that it took us seconds instead of hours or days to get that fitness function. And so with a genetic algorithm, after mutation and crossover, the fittest survive. And we used as our uncertainty quantification technique something that's since been demonstrated in experimental data sets as well to be useful, I think, by the Denmark lab and others. And that's, we focused specifically on the distance in latent space in our artificial neural networks of a new compound to available training data. And the main reason we did that is because I said we could get to 1 to 2 kilocal per mole error with something like our MCDL25 model, but the minute we went out to totally new spaces, new metals, new oxidation states, new coordination environments, our error ballooned. And so in order to control that, what we did was we said, if a point is close to training data in the latent space or the feature space, then we're willing to make that prediction. If it's far, we don't want to make that prediction. And it's really easy to implement that in a genetic algorithm simply by adding a composite fitness function that says we want points that satisfy our design objectives, but aren't too far from training data, either in distance or latent space. And so this first way we did it worked really well. So just the slide I showed you for high throughput screening, we extended it very trivially to open shell transition metal chemistries to explore spaces of, say, 37,000 catalysts. And there we could easily identify ways to break expectations of what it takes to make a good catalyst for methane to methanol conversion. And by using this distance uncertainty quantification, we were able to control the errors. So we were able to avoid increasing our errors significantly beyond the errors that we would get from the test set of the model. And we applied this also to functional materials. But the question is, just getting close to DFT ground truth again doesn't necessarily guarantee that we're close to an experimentally observable material. And so what we wanted to do was, I mentioned that we had studied 23 different DFAs, and we saw that with feature analysis and so on, the DFAs were largely giving us similar design principles. But what we did was we carried out a transfer learning approach where we kept the latent space preserved roughly between the 23 DFAs. And we went out and asked ourselves, what does it take to predict a spin crossover compound? And so again, these were materials where the high spin and low spin splitting are roughly near degenerate. And so what you can see is across the space of around 182,000 candidate materials, if we just pick on one DFA, in this case, it's B3-LIP, it tends to think a much wider space of materials can make a good spin crossover compound than have ever been observed experimentally. What I'm calling experiment on this slide is any text mined structure that could be obtained where spin crossover had been observed that was what the material was studied for. So that's what experiment is here. And then if we instead require that at least 12 of our density functionals agree out of 23, what this means is that functionals from different rungs and from different families have to all agree on this, which actually is quite challenging. Then we can see that the convex hull of materials favored by experiment and by the consensus-based approach are in much better agreement. And in fact, it's in such good agreement that it motivates us to point out that the spaces where the DFA consensus suggests new materials that have yet to be studied experimentally, these turn out to be mostly cobalt nitrogen compounds. And if you take a look, they're relatively underexplored experimentally. So the iron nitrogens are really well known, but where our model is picking up on in the space that where the DFA consensus convex hull exceeds that from the experimental set is largely just these cobalt nitrogen compounds. And so it suggests a path where even though all of the density functional theory approaches are approximate, requiring that they all agree holds them to a higher standard that then allows us to make predictions that are significantly more robust. Now, another thing to think about is that really satisfying one materials objective is not enough, but we usually want to satisfy multiple objectives. And these could include things to do with stability, and in particular, in one application, we were looking at redox flow batteries and what does it take to design a stable, soluble, and high redox potential redox couple for redox flow battery applications. And so rather than focus on retrosynthesis, we built our candidate pool up in a way that would ensure that all of the materials we were exploring were synthetically accessible. We started with 38 heterocycles and fused them together in a way that was relatively simple and straightforward for thinking about for synthesis. And then we want to control solubility in polar non-aqueous electrolytes. So we attached to these different core bidentate ligands around 900 functional groups. And people have studied vanadium to death in these systems. We were interested to know if other earth abundant metals from chromium to cobalt could in turn be attractive redox couples for this type of material system. And in total, all the combinatorics work out that this is now 3 million compounds. So I started my talk at 300 and I'm moving on towards 3 million. And importantly, these are huge molecules. These are, because we're interested in controlling stability and resistance to crossover, these are 100 to 200 atoms in size, the types of calculations I would have never have conceived about carrying out when I was a student, and that are still computationally demanding to carry out to this day. And we used efficient global optimization with the 2D expected improvement criterion to control for solubility and redox potential. And what this means is we put on our two axes that we want to optimize simultaneously, redox potential and solubility, which we addressed via proxy with log P. And I'm showing this as a cartoon, and I'll show the real results on the next slide. So we go out and we pay the price of carrying out DFT calculations because we have no prior knowledge of the space. It takes us probably a couple of weeks to get a couple hundred points. We train a neural net and ask it what it thinks of the space. And then we, if you're not familiar with 2D expected improvement, we go out and we pick out points that are both uncertain and most promising in the space and use that to then go back and collect new DFT data and active learning and so on. And so this is what this looked like in real life. So after 2 weeks of DFT calculations, this is all we could get on about 64 GPUs on my cluster. Again, because these compounds are so big. And then in about 3 minutes, this is what the neural net told us. And you can see where the Pareto front is lit up with high expected improvement scores. And so we go back to DFT again for another week, and we can see that our results were not that impressive because the space is large and the amount of data we had available to the model was relatively small. But after another few minutes with the neural net, and then we go back to DFT again, we can see we do a lot better this time. So our errors are getting much better. But the neural net, the EI score is getting increasingly pessimistic that we have any chance of improving things further. And so after finally about 6 weeks with DFT and about 15 minutes with our neural net, we call it quits. And we ask ourselves, what types of design principles do we see on this Pareto front? And we actually see convergent design principles. It's largely that we want to have a manganese high spin complex with oxygen coordinating atoms and sulfur in the ring and small polar groups. These in large part are design principles I probably could have told you back on slide 9 when I was showing you the porphyrin, because we know redox potential is strongly controlled by molecule size, whereas we want the solubility to be controlled by some degree of polar groups, and that oxygen coordination will strongly drive the manganese towards high spin that will improve redox potential. But that being said, if we looked at how this compared to random search, the distribution here isn't normal. So as a conservative estimate, we did about at least 500 times faster than we would have if we'd done a random search. And the first time I saw this, I thought, oh, there's so much hype in this community, 500 times faster. Everyone's always talking about doing things 500 times faster. And that's until you realize that it took us 6 weeks to do the 500 times faster result. And so this is the difference between having an answer this month versus not in our lifetimes. And so now my group is using this for the design and discovery of active and stable selective CH activation catalysts, among other things. But I want to finish with one quick story about how we've extended this to periodic materials with metal organic frameworks. And in particular, when we got into this, typically people use things like pore geometry to describe gas separation in metal organic frameworks, in large part because when you think about shoving gas molecules into these MOFs, what seems to matter most is pore geometry. But RACs, as you'll recall, are graph-based descriptors that really don't encode any of that information directly. So the first thing we wanted to ask was, do RACs, especially RACs decomposed to different components like the SBU, which is the secondary building unit or metal node, versus linkers and so on, do they help at all for gas uptake? And the answer is yes. And also analysis of the most important features, the most important RACs tell us things like that for CO2, the chemistry of the metal node matters more than it does for methane, because methane behaves more like a rock. And that as we increase pressure at which we're trying to understand gas separation characteristics of why a MUF might prefer methane versus CO2, the dependence on the chemistry actually goes away. And this was all really intuitive and a great way for us to understand how MOFs behave. But we noticed that the conclusions depended really on whether we used a set of synthesized MOFs, so from the core MOF database, versus hypothetically enumerated MOFs that a lot of the community uses. And so we wanted to know why they were different and where they differed the most. And it turns out if you take a look at the experimental set of MOFs, which is called the core MOF database, versus hypothetical MOFs. When you see gray in these plots and these t-SNEs, it means that a hypothetical set doesn't sample a certain type of chemistry, but the experimental set does. And so it turns out when people have been creating these hypothetical sets, they've been really missing a diversity of metal node chemistry. And so it's impossible to reach conclusions that metal node chemistry matters if the variations aren't in the sets. And while we showed this on in this paper on MOF chemistry, I think this is a challenge general to thinking about how do you not limit yourself by past experimental results, but how do you also not limit your hypothetical sets to not directly sample experimental results? And so I think I'm about out of time, but I wanted to mention how we've started to use these insights to particularly think about building machine learning models directly on experimental data, where it would be extremely challenging for us to generate any type of DFT or any type of simulation data. And so we went back to this experimental set I mentioned, the core MOF data set, and we looked at all of the structures and manuscripts we could possibly download with MIT's licenses. And we looked at two challenges for multi-objective materials use in MOF space in terms of making these really robust materials that people like you to use for catalysis, for quantum computing, and so on. And they're just two simple things. One is, if we heat up the MOF material, does it stay in one piece? Does it retain its structure? And MOFs are often synthesized with lots of solvent molecules in the pore. Can we evacuate them? Can we activate the MOF and eliminate those water molecules so we can do things like catalysis? And so what we did was we trained models using those rack MOFs, those racks for MOFs. And what we could do is we could predict stability, what makes a material stable for activation, and what makes a material stable when we heat it. And we could do that same map, that porphyrin abstraction I mentioned, but on MOF chemistry now. And one of the things we found was that what's going on at the linker and the specific linker chemistry turns out to be really important for both of these properties. And there really aren't any heuristics that exist in the experimental literature or prior computation that had really teased apart what effects the linkers have on these two properties, because they just hadn't looked at so many MOFs at the same time as we did. And so then we can ask ourselves, well, what new materials did we not know the ground truth for yet that we can make predictions on their stability, and where can we find new stable materials? And what we can do with this is things like screen 1,500 unseen materials, which the ML models are confident on, in about a few minutes to an hour, which is dramatically faster than you could imagine carrying out these experiments or doing the calculations. So I will skip over this and just finish up and conclude by saying we started in my group as a computational chemistry group interested in accelerating high throughput screening for open shell transition metal chemistry. This naturally led us to realize that high throughput screening is still not fast enough to really address design challenges. This led us to train the first machine learning models to predict open shell transition metal complex properties such as quantum mechanical ground state spin. And just making more accurate ML models is not so interesting unless you can accelerate the discovery of materials and reveal design rules. Everything I've described is on Conda and GitHub, as well as in a website. The MOF models I described at the end are also on a website, a different website in a beta. If you're interested, just contact me offline. And I'd like to finish by acknowledging the students who did the work. The MolSimplify work was started by Tim Ioannidis. The machine learning work was started by John Paul Janae in my lab. And then I've had the pleasure of telling you about some of the work carried out by my two senior graduate students, Aditya Nandi and Chen Rudwan. And I'd like to finish by acknowledging the funding sources. And thank you all for listening.
Thank you for this great talk, Professor Kulik. So we have one clarifying question in the chat Q&A box. Can you please name the Cambridge package you were referring all this while?
I didn't follow the end of that question.
Can you please name the Cambridge package you were referring all this while? Some anonymous attendee asked.
Which Cambridge package?
Maybe we can ask him to clarify it.
So I referred, go ahead.
No, you go ahead. Yeah. You referred to some Cambridge package that was used in your data processing.
No. So I referenced the core MOF data set, which is a subset of the Cambridge structural database, but everything we use is our own code, which is for high throughput screening. So I don't know what you mean on, for instance, this slide, another group, so a group of people originating from Randy Snur and Baron Smith took a piece of the Cambridge structural database and used that to represent the experimentally synthesized metal organic frameworks that have been known and crystallographically. Is that what you're referring to?
I asked the question, the person to clarify a little bit, maybe he or she will clarify later. But we have another question from another anonymous attendee. Thanks for the very interesting talk, Professor Kulik. On slide 8, you mentioned a significant improvement in ML bond distance estimation with ANN relative to UFF. How about geometries at the metal center? Did you also consider that?
So we only ask our neural net to predict the metal ligand bond length, and so it can do interesting things like predict, but it's not say a neural net potential. It predicts across all of transition metal chemical space, and so as that compromise, all we ask it to do is predict a series of metal ligand bond lengths, and so it can do neat things like it can predict the existence of Jahn-Teller distortion, even if we don't tell it Jahn-Teller distortion exists. But everything else, like say the organic ligand around, we ask a force field to predict. So we're not asking the model to make predictions about the, say, metal ligand angle, but we probably just as easily could if that were something that we wanted to predict.
Okay, so there is another question from an anonymous attendee. The DFT with all functionals reported treat extensively the static correlation. However, most of these systems are strongly correlated systems requiring a proper treatment of the dynamic correlations. The agreement among different XC may indicate that for that system, the single determinantal WF is good to capture the right physics. But how can we be sure that the argument is really an indication of a more reliable calculation? Could the physics be still wrong while all predictions agree?
So part of that question was wrong, but that aside, so I would love to put on my other hat and tell you about our other work. So we have a series of papers where we detect the existence of strong correlation and we show where it's present and where it's not. And so the answer is that sometimes it's present in these transition metal complexes, sometimes it's not. That's a whole different talk I don't have time for. But it's been shown by us and others that things like PBE or like an LDA do a really good job of inherently treating or allowing for multi-determinantal character by overcompensating the degree of delocalization error. Like basically the excess delocalization error in things like the lowest rungs, the GGAs, in turn mimic what you would want out of a multi-determinantal solution. So that's a third hat and a third talk I'm not going to cover. But the fact that you have things with a lot of potential static correlation error, that is exactly correct. Like the double hybrids are going to be prone to static correlation error. I think where the question misspoke is that these different DFAs are aiming to correct self-interaction error and doing so at the cost of introducing static correlation error. And what they handle well is they handle well the dynamic correlation, especially the ones that are in the double hybrids. So the fact that they all agree, I agree that's not enough, but I didn't have time in my talk to cover how we've done that. But if you're interested, feel free to check out some of our papers. Basically, what we've shown is that you can detect multi-reference character using the same machinery, and you can identify hot spots and cool spots where it's safe to run these DFT calculations with one functional or another functional, and where it's unsafe in other cases. Unfortunately, I already put too much in my talks and I had to cut that for today, but I encourage you to check that out.
Thank you. Thank you for the nice talk. Yeah.
Yeah,
We
again,
have one more question, maybe.
Okay. Yes. Okay. I think Ludic asked, thanks for the great talk. You just mentioned that your ML model could predict Jantler effects without being told that there are Jantler effects. Do you mean that Jantler effects are not present in the training data?
Oh, I do mean that they're in the training data, they're not controlled for, they're not labeled in any way. When the neural net predicts asymmetric bond lengths, that's evidence of strong Jantler distortion being present. And so the ANN can predict that. That's something that's actually really challenging for force fields and semi-empirical models to get right unless you tell them beforehand. What was in the diversity of the data set is present, and that's where the model is learning that from. It's not learning it from thin air. Thanks for the clarification.
Okay.
Thank you.
So with this, we think we will end our session and hand over to Rajat, and we are also on time today.
Yeah, I mean, thank you so much to all our speakers, and especially Professor Kulik, because I know that she is attending several other conferences, but she still managed to find a slot for us and give us such an exciting talk. And tomorrow we are going to have day 6 and also the final day of this VISTA Symposium. And I do hope that we will continue to have the same love and affection that you bestowed on us for last 5 days. And I hope that not only you and also your other friends will be joining us tomorrow. And with that, I want to end today's session and see you all tomorrow the same time. Thank you very much.